College Algebra, Module 10, Topic 10.1, Logarithmic Functions and Models. Objective 1, Logarithmic Function Definition. The logarithm with a base a of a positive number x denoted by the log of x base a is defined by log of x base a equals k if and only if x is equal to a to the k, where a is greater than 0, a is not equal to 1, and k is a real number. The function given by f of x equals the log of x base a is called the logarithmic function with base a. The logarithm, or sometimes we'll just call it the log, is simply the power to which you are raising the base. Let's go back up here to the opening definition. The log of x base a equals k. The base is this really small number. That is just what the base has always been. The number that the log is equal to, which in this example is k, is the power that we raise to get x, or this number right here. So when you think log, just think the log is the power to which you're raising the base. The domain of a logarithmic function is x is greater than 0. That is, the log of x is undefined for x less than or equal to 0. For example, find the domain of the function f of x equals the log of 3x plus 2. Well, this is your x, basically, that you're looking for the domain. So for this problem, 3x plus 2 has to be greater than 0. So if we subtract 2 from both sides, we get 3x is greater than negative 2. Dividing by 3, we get x is greater than negative 2/3, which means for our domain of this function that x has to be somewhere between negative 2/3 and infinity. We could verify this graphically as well. If we go into our calculator and go to y equals and enter the log of 3x plus 2 and graph that, notice we have a graph from negative 2/3 all the way to the right, but notice there's nothing back to the left of negative 2/3. That means when you put it in the function, it gives you an answer that is undefined or not real. Let's do another example. Find the domain of the function f of x equals the log of x squared minus 6x plus 5. Well, to find the domain, we're going to take the value that we're taking the log of and find what makes that greater than 0. Well, to solve a quadratic inequality, we're going to go through and set it equal to 0. Well, to solve this, I'm going to factor, so we would get x minus 1, x minus 5 equals 0, which gives us our negative 1x and our negative 5x, which gives us our middle term of negative 6x. Setting each factor equal to 0, we get x minus 1 equals 0 or x minus 5 equals 0, which gives us x is equal to 1 and x is equal to 5. So if we were going to graph that, we know that it crosses the x-axis at 1 and 5. Because it's a positive x squared, we know it opens up, so we know our parabola goes down something like this right here. So if we're trying to find where it's greater than 0, that means it's greater than 0 for all values less than 1, and again for all values greater than 5. So our domain would be the interval from negative infinity to 1. It cannot include 1 because 1 would make it equal to 0, joined with the interval from 5 to infinity, and again I'm going to put a parenthesis on 5 to show that it cannot equal 5 because that would make it equal to 0. Now we could do this one on our calculator as well. So when we type in our function, the log of x squared minus 6x plus 5, and graph it, Notice there are values from 1 to the left and again from 5 to the right. Now let's do some more examples. Find the value of each of the following. The log of 36 with a base of 6. Well, remember, log means find the power. Our base is 6, so this means 6 to what power would give us 36? Well, we know that 6 to the second power is 36, so the log of 36 base 6 is equal to 2. Okay, now let's switch it. Now let's do the log of 6 base 36. Well, that means 36 to what power would give us 6? Well, we know that the square root of 36 is 6. The square root of 36 can be rewritten as 36 to the 1/2 power, so the log of 6 base 36 is equal to 1/2. The log of 32 base 2. Again, the base is 2. We are looking for the power of 2 that would give us 32. Well, 2 to the 5th is 32, so the log of 32 base 2 is equal to 5. And again, the log of 2 base 32. That means 32 to what power is 2? Well, remember 2 to the 5th is 32, so the 5th root of 32 is 2. So that means 32 to the 1/5 power is 2. So the log of 2 base 32 is equal to 1/5. And I will show you how to do these on your calculator shortly. The log of 1 over 36 base 6. Well, always start with the base, so that means 6 to what power would give us 1 over 36? Well, 36 is 6 squared, so that means 6 to what power would give us 1 over 6 squared? Well, 1 over 6 squared can be rewritten as 6 to the negative 2. So 6 to what power equals 6 to the negative 2? So that would be negative 2. And then the last one, the log of 1 over 32 base 2. Base is 2. You're looking for the power that gives us 1 over 32. Well, 32 is 2 to the 5th, so that means 2 to what power is 1 over 2 to the 5th? 1 over 2 to the 5th can be rewritten as negative 5 power. So we know that the log of 1 over 32 base 2 is equal to negative 5. Now we're going to look at two special bases. The first one of these is the common logarithm, and it says the common logarithm of a positive number x, denoted log of x, is defined by the log of x equals k if and only if x is equal to 10 to the k power, where k is a real number. All this means is that the log of x has an understood base of 10. Now the function given by f of x equals log of x is called the common log function. The second type of special base is the natural log, and it says that the natural logarithm of a positive number x, denoted ln x, is defined by the natural log of x equals k if and only if x is equal to e to the k, where k is a real number. The function given by f of x equals ln x is called the natural logarithm function. Okay, so what we've got is we've got the log of x to some base. We've got just the log of x, which when you see that means the base is 10. And we've got the natural log of x, which means the base is e. So let's do some examples. Find the value of each of the following. The log of 100. Well, remember, we just found out that the log, if there's no power in here, is understood to be 10. So that means 10 to what power is 100? Well, 10 to the second is 100, so the log of 100 is equal to 2. The log of 10,000, that means 10 to what power is equal to 10,000? Well, 10,000 is the same as 10 to the fourth, so 10 to the fourth power is 10,000, so the log of 10,000 is 4. Now the log of 0.001, sometimes I think it helps to write this as a fraction, so 0.001 tenths, hundredths, thousandths is the same as 1 over 1,000. Well, 1,000 is the same as 10 to the third, so that's the same as 10 to the negative third. So the log of 10 to the negative third means find the power that we're raising 10 to get 10 to the negative third, so that answer would just be -3. What about the natural log of e? That means the base is e, so e to what power just gives us e. So the natural log of e is just 1. The natural log of e to the third means find the power when the base is e, and that would just be 3. Objective 2. Properties of exponential and logarithmic functions. The first property says the log of 1 base a is equal to 0. That means find the power that we raise anything to get 1. Well, if the base is a, then if you're saying that the log is 0, that means the power is 0. Well, anything to the 0 power is 1. The second property, the log of a to the x base a is equal to x. Well, remember, the base is a. The answer to the log is the power, so a to the x gives us a to the x. So it's sort of like the base a and a to the power, sort of like they just cancel to give us x. And then the third property, a to the log of x base a is equal to x. Again, it's like if you have a to the power and a log base a, they just cancel and we get an answer of x. So these are just some properties that are going to make life easier when you go to start solving these equations and simplifying expressions. So use the properties to simplify the following. The log of 6 to the fifth base 6. Well, if we tried to work it out, the base is 6. Log means we're looking for the power to give us 6 to the power of 5. Well, that just means that the log is 5. The log of 1 over 7 to the fourth base 7. Again, that's like saying the log base 7 of 7 to the negative fourth. Well, that just gives us -4. And 8 to the power of log of 45 base 8. If we have a log base 8 and a base of 8, then our answer would just be 45. Okay, I haven't forgot about showing you how to do these on the calculator. So objective 3 is how to use your calculator to do logarithms. Well, the TI-83 or 84 plus evaluates base 10 logs and base e logs. Okay, the log key, which is down beside the 7, finds the value of common logs. And then the natural log key, which is right below the log, finds the value of natural logs. And remember the difference. Log is base 10, natural log is base e. So let's do some examples. Evaluate the log of 1,000 and round to the nearest hundredths if necessary. Well, to do it the regular way, that's the log base 10 of 1,000, which means 10 to what power would give us 1,000, which 1,000 is 10 to the third, so that answer is going to be 3. Now on our calculator, we're just going to type in the log of 1,000 and we get 3. The log of 345, now that's a different story. That means 10 to what power would give us 345? Well, there is absolutely no way to know that. We're going to do the log of 345, and that gives us 2.54 if we round to the nearest hundredth. The next one, the log of 1.67, again, we're just going to type it in, the log of 1.67, and we get 0.2227, or rounded to the nearest hundred would be 0.22. Now to check that, we would say 10 to the power of 0.2227, so let's check that. 10 to the power of 0.2227164711, and it gives us 1.67. This time we're doing the natural log of 3.4. Well, we're going to go to natural log of 3.4, and we get 1.22. The natural log of 478. The natural log of 478, which is 6.17. To check it, that would be e to the power of, so we're going to go second e to the power of, and I'm just going to type in the 6.17. Remember that we're rounding, and that gives us pretty close to 478. And then the last one, the natural log of 0.00234, natural log of 0.00234, and we get negative 6.06. Now notice it's okay to have negative answers, we just can't take the log of a negative number. Objective 4 is the change of base formula. Now the change of base formula allows you to use the calculator to find the value of logs with bases other than 10 and e. And the change of base form says the log of k with a base a can be found by doing the log of k divided by the log of a, or even the natural log of k divided by the natural log of a. So let's do an example. Evaluate the log of 72 base 5, which means 5 to what power gives us 72? Well, we have no idea, so the change of base formula says we're going to do the log of 72 divided by the log of 5. So the log of 72 divided by the log of 5. And when we do that, we get 2.66. To check it, that would be 5 to the power of 2.66, which is pretty close to 72. Okay, again, the log of 89 base 2. Our formula says the log of 89 divided by the log of 2. 89 divided by the log of 2, 6.48. And just to show you, that's the same if we went the natural log of 89 divided by the natural log of 2, and we get exactly the same thing. And then the last one, the log of 100 base 1/6. Well, that is the log of 100 divided by the log of 1/6, which gives us negative 2.57. Okay, objective 5, logarithms and equations. Well, there's going to be a time that you need to change from log form to equation form and equation form to log form. Well, the property that you need to remember is y equals a to the x if and only if x equals the log of y base a. Now if you will remember, the base is a, the answer to the log is the power, and the result is that big number right there. That's exactly what this says right here. Okay, now as a note, if we are doing natural log, that means x is equal to the log base e of y, which means e to the x is equal to y. Okay, so we get e to the x equals y if and only if x is equal to the natural log of y. So these next examples, write each of the following as an equivalent statement. 125 equals 5 to the third. Notice your base is 5, so that means the log of the big number, the log of 125 with a base of 5 is equal to 3. Remember, the answer to the log is the power. The next one, the log of 32 base 2 equals 5. The equivalent statement here, because they're giving us the y and we want to write it as a power, is 2, that's our base. The answer to the log is our power, equals 32. Now it's pretty easy as long as we're just doing numbers because we can check our work. But what about if we start doing variables? E to the fourth power is equal to p. What does that mean? Well, the base is e, so that means it's the natural log of the answer equals the power. So e to the fourth equals p can be rewritten as the natural log of p is equal to 4. And then the last one, 7 equals the natural log of 8x. Well, natural log means the base is e. The answer to the natural log is the power, so that means e to the 7th is equal to 8x. Objective 6, solving logarithmic equations. To solve an equation of the form, the log of x base a equals k, we're going to exponentiate both sides with a base of a. So to do an example, the log of x equals 9. Well, if we knew what this number was, we could just type it in our calculator. We're trying to find the log of what number is equal to 9. Well, the base is 10. So what that means is 10 to the 9th power is equal to x. So our base was 10, so basically we're going to put an exponent on both sides. So we would have 10 to the log of x equals 10 to the 9th. Well, 10 to the log of x, that was our property that just said we get x, and we get 10 to the 9th power. So our answer for this one is a 1 with 9 zeros. And this is one we probably don't have to do it on our calculator. Now this example, solve for x. The log of x base 2 equals 6.2. So what that means is, let's do 2 to the power of on both sides. So we would get 2 to the log of x base 2. Well, 2 to the power and base 2 cancel and we get x. So then we've got 2 to the 6.2 power. Sometimes you can just go ahead and write it in the equivalent form. The base is 2 to the 6.2 equals x. Either way you like to do it. So then we're going to need our calculator, and we would get 2 to the power of 6.2 x to be equal to 73.52. Next example, the natural log of x equals -2. Well, the base is e, so what we do is we put both sides with a base of e, so e to the natural log of x, well that just is our property that says that's x. The other side, e to the -2, so we need to punch it in our calculator, second e to the power of -2, and we get x is equal to 0.14. And then our third example, the log of 64 base x equals 3. Well, this time our base is x, so we've got x to the power of on both sides. So the left side is going to be 64. The right side is going to be x to the third. Well, what to the third power would give us 64? So we know that x is equal to 4. Objective 7. Solving exponential equations. To solve an equation of the form a to the x equals k, take the base a log of each side. Well, if we think about the equivalent form of a to the x equals k, that means the log of k base a is equal to x. So that means we are going to, if we start with a to the x equals k, we're going to do the log base a of this side and the log base a of this side. So the log base a of a to the x is just x. Over here, the log of k base a, well, we don't know what it is, so we're going to say the log of k base a. So we've got our equivalent equation form, or we've got our procedure that says if they give us exponential form, we take the log base a of both sides. So our example is solve the equation e to the x equals 9. Well, our base is e, which means we are going to do the natural log of both sides. Well, the natural log of e to the x is just x, so we have to find the natural log of 9. So on our calculator, we are going to do the natural log of 9, and we get x is equal to 2.197 or 2.20. And remember, we can check it, go back and plug it in place of x. Now the next example, solve. This time we're going to round to the nearest thousandth. 6 to the power of x equals 20. Well, because we have a 6 to the power, we're going to do the log of both sides, but we've got to do log base 6. Okay, so we're going to take the log base 6 of both sides. Well, on this side, the log base 6 and a base of 6 cancel, and we get x. On this side, it's the log of 20 base 6, so we're going to have to do our change of base formula, and we would get the log of 20 divided by the log of 6. So when we type it in our calculator, we do the log of 20 divided by the log of 6, which is 1.6719. Thousandths is 3 decimal places, so we would get 1.672. Now to check it, we're doing 6 to the power of 1.672, and we want to show that we get an answer of approximately 20, which we do. Now let's do another one. 10 to the power of 2x is equal to 1,000. We're going to do a log. We're going to do a log base 10 on both sides. So that would be the log base 10 of 10 to the 2x equals log base 10 of 1,000. Well, the left side, we just get 2x. On the right side, we get the log of 1,000 base 10. Well, 1,000 is 10 to the third. So that would be the log of 10 to the third base 10. So that side is just going to be 3. So we get 2x is 3. Divide by 2, divide by 2. So x is 3 over 2. Now, let me show you a different way to do this one. Because we're looking at same bases, we have 10 to the 2x on one side. 1,000 is 10 to the third. Well, think about it. If we want 10 to the 2x to be equal to 10 to the third, that means 2x has to be 3, which means x has to be 3 over 2. But now that one only works if we're dealing with the same bases. Okay, you are now ready to do the homework for topic 10.1 in my math lab. If you have any questions, let us know.